The universe is filled with stars of different types and are classified based on color, temperature, size, composition, and brightness. Based upon the mass, the stars in the universe are of different types. They are
Hypergiants. A hypergiant is a star with an enormous mass and luminosity. It belongs to luminosity class 0. It shows signs of a very high rate of mass loss by stellar winds every second. Hypergiants are the largest stars in the universe, usually larger than supergiants. VY Canis Majoris and Stephenson 218 are red hypergiants.
number 2, supergiants. The massive and the most luminous stars in the universe are the supergiants. The temperature range of supergiant stars spans from about 3400 Kelvin to 20,000 Kelvin. Supergiants develop when massive main sequence stars run out of hydrogen in their cores, at which point they start to expand just like lower mass stars.
After they have exhausted their hydrogen and continue fusing heavier elements after helium exhaustion such as carbon, oxygen, silicon until they develop an iron core, at which point the core collapses to produce a type 2 supernova. After the supernova, the remnant left is a neutron star. If the remnant has a mass greater than about 3 solar masses, it collapses into a black hole.
Rigel star is a blue-white supergiant and Betelgeuse star is a yellow supergiant. Number 3. Giants. Giants are more massive, luminous and have a larger radius than the main sequence star. Giant stars have radar up to a few hundred times the Sun and luminosities between 10 and a few thousand times that of the Sun. Even our Sun, after its stable lifetime, may turn into a red giant star. Number 4. Main sequence stars.
Stars like our Sun, which are the most numerous true stars in the universe. It generates thermal energy in its dense core region through the nuclear fusion of hydrogen into helium. These include dwarf stars and yellow dwarfs like our Sun and red dwarfs like the one which is closest to our solar system like the Barnard star.
Number 5. Faint death stars. These includes neutron stars, brown dwarf, and white dwarf.
Wind's law relates stellar color to stellar temperature. Blue colors dominate the visible light output of very hot stars. On the other hand, cool stars emit most of their visible light energy at red wavelengths.
In general, the more massive the star is, the shorter its lifespan on the main sequence. As compared to main sequence stars, the lifespan of the hypergiants are shorter.
After the hydrogen fuel at the core has been consumed, the star evolves away from the main sequence on the Hertzsprung-Russell diagram into a supergiant, a red giant, or directly into a white dwarf.
The solar system is quite large as compared to Earth.
Jupiter is a sub-brown dwarf, which means it has all the same materials as the Sun and formed in the same manner as stars and brown dwarf, but that has a mass below the limiting mass for the thermonuclear fusion of deuterium.
It is more than twice as massive as all the other planets combined. Jupiter's immense volume could hold more than 1,300 Earths. That means if Jupiter was the size of a basketball, Earth would be the size of a grape. But Jupiter is much smaller when compared to the Sun.
The Sun is quite large that it could fit around 1000 Jupiters. The Sun.
The Sun is a G-type main sequence star that comprises about 99.86 of the mass of the solar system. The Sun is estimated to be brighter than about 85% of the stars in the Milky Way, most of which are red dwarfs.
The Sun is neither solid, liquid, nor gas, but plasma. A plasma is a soup of positively charged particles called ions and negatively charged particles called electrons, in which electrons flow freely away from the atoms.
The formation of the Sun may have been triggered by shock waves from one or more nearby supernovae. This is suggested by a high abundance of heavy elements in the solar system, such as gold and uranium, which are produced in extreme conditions, such as a supernova.
The Sun's mass is approximately 2 into 10 raised to 30 kg. Because of its mass, the Sun has tremendous gravitational pull, which allows to hold a system of 8 planets, dozens of dwarf planets, 170 moons, and many asteroids and comets.
Parts of the Sun. Number 1. Corona. The corona is the outer atmosphere of the Sun. The temperature in the corona is 500,000 Kelvin or more, up to a few million Kelvin, which is hotter than the surface of the Sun, which is 5500 degrees Celsius or 5780 Kelvin.
It extends many thousand kilometers above the visible surface of the Sun, gradually transforming into a solar wind that flows outward through our solar system.
The transition region is a very narrow 100-kilometer layer between the chromosphere and the corona, where the temperature rises abruptly from about 8000 on the surface to about 500,000 Kelvin in the Sun's atmosphere. Number 2. Chromosphere. The chromosphere is a layer in the Sun between about 400 km and 2100 km above the photosphere.
The temperature in the chromosphere varies between 4000 Kelvin and 8000 Kelvin, but in this layer, the temperature decreases from top to bottom, unlike the inner layers. The common feature is the presence of specules, some of which are even larger than the Earth. It is a dynamic jet of plasma associated with regions of high magnetic flux.
Number 3. The photosphere. The photosphere is the deepest visible layer of the Sun. The temperature in the photosphere varies between 6500 Kelvin in the bottom and 4000 Kelvin at the top, which is 6200 and 3700 degrees Celsius.
Most of the photosphere is covered by granulation caused by convection currents. Granules completely make up the photosphere and are the features that receive and radiate light. Granules, which are typically 700 to 1000 kilometers in diameter above the width of Texas, appear as bright areas surrounded by narrow darker regions that last for about 5 to 10 minutes. There are even supergranules, which could fit 2 Earths and last for about a day.
The upper 70 km of the photosphere is where the Sun starts to turn transparent and photons can finally escape into space as sunlight. When they reach the outer 70 km, the atoms cool sufficiently to radiate the photons into space.
Number 4. Convective zone. The bottom of the convective zone is heated by the radiations coming out of the radiative zone. The temperature at the bottom of the convective zone is therefore high, which is 200,000 degrees Celsius. At the same time, at the top of the convective zone is being cooled by the creation of light by the escape of photons. So, the temperature at the surface is only 5700 degrees Celsius.
This difference in the temperature results in a physical phenomenon called convection. The energy is transferred by convection. The interaction of the convective turbulent motions of the gas in the convective zone and the differential rotation leads to the generation of electric currents and extensive solar magnetic fields. This process is called the solar dynamo mechanism.
Number 5. The radiative zone. The radiative zone extends about 3/4 or 75% of the way to the surface. The temperature of the radiative zone ranges from 2 to 7 million degrees Celsius. The radiative zone is the site where energy transport occurs. The plasma density here is very high.
This zone can be categorized as the place where the photons bounce around, facilitating the ability for energy to be transported to the outer surface of the sun. So, the radiation does not travel directly outwards in this part, and the radiation gets bounced around countless number of times, forming a zigzag path outward. It takes several 100,000 years for radiation to make its way from the core to the top of the radiative zone.
Photons can travel only a short distance before they are absorbed or scattered by another particle, gradually shifting to a longer wavelength as they do. For this reason, it takes an average of 171,000 years for gamma rays from the core of the sun to leave the radiative zone.
Number 6. The core is the hottest part of the sun and of the solar system. It is compressed by the weight of the layers of the sun above it. It has a density of 150 gram per centimeter cube at the center and a temperature of 15 million degrees Celsius or Kelvin, and extreme pressure of 26.5 petapascals, possible enough for fusion to occur.
The sun is burning with the nuclear reaction by burning hydrogen atoms into helium atoms in its core. It's not the combustion which takes place in the sun, but the fusion process. Most of the sun's released energy is through the proton-proton chain reaction. It burns through 600 million tons of hydrogen and converts it into 596 million tons of helium per second.
For comparison, the mass of the Earth is about 1.35 into 10 raised to 21 tons. It would mean the Sun consumes the mass of the Earth in about 70,000 years,
which is equivalent to 1 trillion nuclear bombs per second. The remaining 4 million tons of hydrogen is converted to energy. According to Einstein's famous equation from special relativity, E equal to mc square, mass and energy are equivalent. Energy can be gained from using a very small amount of mass, because when we square C, we get a very large number, which is 9 into 10 raised to 16 meter square per second square. The sun cannot convert all of its mass to energy, but it is limited to convert only 0.7% of its mass to energy in the thermofusion process.
Few billion years later, after Sun's death, the solar core will remain as a white dwarf. The Sun is composed of 91% of hydrogen, 8.9% of helium, and 0.1% of heavier elements, and it contains approximately 10 raised to 57 atoms of hydrogen.
At any moment, the sun produces 3.854 into 10 raised to 26 watts, but only 1.74 into 10 raised to 17 watts reaches Earth, but most of them radiates into space.
Life cycle of the Sun. Our estimate of the lifetime of the Sun is therefore 10 billion years, since we know that the Sun is approximately 4.6 billion years old. The Sun is currently just under halfway through its stable lifetime.
After its stable lifetime and eventually run off the hydrogen gas fuel, the Sun goes through its red giant phase and turn into a red giant star, expand and engulf the inner planets, possibly even Earth. During the phase, it will puff off its outer layers and then settle down as a compact white dwarf star, then slowly cooling for trillions of years to come.
Thank you, and don't forget to subscribe our YouTube channel.